Hello. Let's talk about another behavior of waves. In this case, something called the Doppler effect. Now, the Doppler effect was discovered by a man named Christian Doppler, who was trying to determine what happens when a wave or an observer is moving. Now, you might be familiar with this technology from Doppler weather, which uses the same idea. Any wave can exhibit the Doppler effect. However, we are most used to it in normal life with sound, and that's where we're going to talk a little bit about this. Notice that when a wave is produced, let's talk about a sound wave in this case, from a source that is not moving, the waves will start and spread out concentrically. So as it starts here, it spreads outwards. And notice the distance between each wave is consistent. The wavelength, the frequency would be the same for the wave. The amplitude does decrease because as you move further away from the center, it is spread out more. The energy needs to be spread out more. So as you move further away from a source, it does get quieter. But without movement, the distance between waves is consistent. The wavelength is consistent. Therefore, the frequency stays the same. On the other hand, if the source were to move, you would see the waves start bunching up. So notice here that as the wave moves, on the right-hand side, there's a bigger distance between the waves. There's a greater wavelength. On the right-hand side here, there's a smaller distance between the waves, therefore a smaller wavelength. The waves are still produced the same amount of frequency, so you see a circle being produced the same amounts as circles being produced when it's not moving. So the wavefronts bunch up on the right and they spread out on the left when the source is moving. This is the idea of the Doppler effect. If you bunch up the waves or spread them out, there'll be a shift in their frequencies, an apparent shift in frequency due to the source or the observer moving. This would happen if you are moving or if what's producing the sound is also moving. If you're in front of the wave, let's say you're over on this side, the waves coming at you are closer together, so you therefore experience a shorter wavelength and therefore a higher frequency. If you're behind the wave on this side, the waves are now further apart, therefore there's a longer wavelength, a greater wavelength, and you'd experience a lower frequency. With sound waves, the way that we interpret frequency is through the concept of pitch. So as it's an object that's coming towards you, you would have a higher pitch. It would sound a higher pitch. When the object moves away from you, it's a lower pitch. You most commonly might experience this with, say, a fire truck or a police siren, for instance. Notice that when the truck comes towards you, it's a higher pitch, and then immediately when it leaves and goes away from you, it drops in pitch to a lower pitch. So when it is coming towards you, you experience a higher pitch. When it's away from you, it's a lower pitch. The siren itself is in motion, bunching up the waves on one end versus the other. But if you were actually inside the truck, it would sound normal. So while on the outside, while you are observing it, as it drives towards you, the pitch is higher. As soon as it passes you, it drops. But inside the truck, since you're not moving relative to the siren, it would sound normal. The sound being produced is a normal sound. It's just being shifted because it's in motion. One of the more extreme examples of this might be something that's flying faster than sound or at the speed of sound. So as planes move, they can move several hundred miles per hour. And what will happen is that waves will start bunching up in front. If you travel at the speed of sound, as you produce new waves, the wave front starts building up and building up and building up here, and you end up with a very large pressure wave up front. If you travel faster than the speed of sound, you also produce the same kind of idea, but now you're making basically a cone behind it. This is the idea of a sonic boom. A sonic boom is where you are traveling fast enough to the speed of sound, or faster than the speed of sound, and you're producing a shock wave, where you have a large wave built up behind you that when it hits an observer will hit it all at once. So let's say we're talking about a plane flying. If you've ever experienced a sonic boom, you might see the plane before you hear it because the plane might be traveling faster than the speed of sound. It's traveling before the wave itself. So if you were to look at a plane flying past, you might see that it's producing a pressure wave behind it, basically a wave of air. That would be a sonic boom. So when a plane flies by, you might see it before you hear it because the sound wave is behind the plane. Only when the wave catches up to you do you hear it. Because all the waves have bunched up, you hear a large boom all at once, and then after the boom, you'll hear normal sounds because of the rest of the waves catching up to you. Now, even though we are most used to the Doppler effect with sound, any wave could experience the Doppler effect. That includes light. Now, this is a little bit more extreme, and we often only see this in the case of astronomy. However, light can be shifted, whereas sound, the frequency goes with pitch. With light, it's color. So when we're talking about the Doppler effect with light, we're really talking about a shift in color. But again, the same idea. If it is moving towards you, the waves will be bunched up. And if it's moving away from you, the waves will be spread out. Remember that the colors of the rainbow are Roy G. Biv. That's red, orange, green, blue, indigo, and violet. However, technically, violet isn't really a color. It was actually blue. And blue is really cyan. We'll discuss that more in another video when we talk about colors. So when we're talking about shifting for light, we're really talking about the colors red and blue, not higher and lower pitch. When it's coming towards you, we call it blue because it's the higher end. And away from you, we call it red because it's the lower end. So when an object heads away from you, the object is red shifted towards the red scale, the lower end. And when the object heads towards you, it is blue shifted or shifted up towards the higher end of the scale. However, this is not to say that the colors are automatically going to be red or blue. Elements produce their own unique fingerprint of color, and that is based on the movement of electrons inside the atom, which will be covered in a different video. But let's say that an element is able to produce this spectrum. What that means is these colors here are in the yellow-green range. If we redshift it, it doesn't make the colors automatically red, it just pushes it towards the red end of the spectrum. If it's blue shifted, the colors still may remain yellow or green, but they're shifted towards the blue end of the spectrum. So just because something is red shifted, it doesn't make it turn red, it just makes it more reddish or more towards the red end. This is also definitely true of light that isn't even in the visible range. So if we are talking about something that is ultraviolet rays might be red shifted, making them actually end up being blue. because that's what's beyond the blue end. So red shifted and blue shifted are just the terms we use for these. It does not mean they automatically turn red or blue, just towards the lower end of the scale or the higher end of the scale. However, this is important to us because when astronomers started looking at the galaxies all around us back in the early 1900s, they discovered that almost all galaxies out there show red shifting. This was discovered by an astronomer named Hubble back in the early 1900s, for which the Hubble telescope is named. From that information, that all the galaxies around us appear to be moving away from us, that was one of the major reasons why people started looking into something like the Big Bang Theory, that everything is moving away, and that the further away they are appears to be a greater redshift, so they are moving away even faster. However, not all galaxies are moving away from us. If you look at the Andromeda galaxy, which is within our local cluster, it actually looks like it's moving towards us. We can see by looking at the blue shift of its light. And we can say that in about 4.5 billion years, it actually will collide with our galaxy. Now, because the galaxy is mostly empty space, we don't actually anticipate anything running into each other, but it will be a pretty spectacular show from a distance. Don't worry about it. In 4.5 billion years, the Earth will probably be long dead, so we won't really be around to see it unless we've left the planet, but it's still pretty interesting. So the Doppler effect happens because a source or you are moving. The waves are getting bunched up or spread out. With sound, that means a change in pitch. Towards means higher pitch. Away from you means a lower pitch. With light, that means color. So if an object is moving towards you very fast, it'll be blue. Or away from you, it'll be red.